Hey guys, Mr. Barnes here, bringing another video. This one on Snell's Law. So Snell's Law is a common topic, and excuse my blue hands here. I was coloring with my toddler earlier. Snell's Law is a topic in physics. You've probably done it in like a wave unit, and it has to do with light. So the thing about light is that it has a speed of 3.0 times 10 to the 8 meters per second. So this is in ideal conditions is what I'll call it. So like in a vacuum, or we can also assume like in air, but generally in a vacuum. When light passes through other mediums, it's not going to go as fast. So what ends up happening here is we get a bending of the light. So if you have, say, let's call this water right here, and this is air. So if light's going to shine down here, and air is a fast medium, and water is what we would call a slow medium, so this light is actually going to bend, and we can sort of picture this line right here called the normal line. And light's actually going to bend when it goes from a fast to a slow medium. It's actually going to bend towards this normal line. So I remember how I remembered that, and I wrote it down for myself, is I remember this acronym, SFT. So fast, slow, towards, FST. So when light shines in from air to water, it's going to actually bend towards the normal line. Now if I had the opposite scenario, so I'll draw sort of the similar idea. Here's the wave, and I'll write water and air again. And I'll draw my normal line first this time. So if I have, again, I have a slow medium in water and a fast medium in air, and the light comes up this way this time. So there's something down here that the light is reflecting off. Perhaps it's a fish, and the light comes up this way. So I remember slow. So it goes from a slow, fast. So SFA. It moves away from the normal line. So it actually bends this way, just like that. So when we have a situation where it goes from a slow to a fast medium, we have the possibility of what's called total internal reflection. So total internal reflection is when light stays within a medium. So if we have, let's use the exact same situation. And I just happen to know off the top of my head that the critical angle for light is 49 degrees. So I'll explain what a critical angle is now in a second. So I'm going to draw in this critical angle right here. So there it is. 49 degrees, just like that. So that's my critical angle. So this is water and air again. So if I have, let me see if I can't find a different color marker here. So if I have a light coming in here at an angle that's less than 49, what's going to happen is it's going to pass through the medium. So it's going to go like that. If I have light that's coming in greater than 49, so somewhere down here, what's going to happen is it's actually going to reflect within that medium. So it doesn't pass through, it bounces off that boundary. And if light happens to come in at exactly that critical angle of 49 degrees, it's going to actually just reflect along that line. And that is what total internal reflection is. And this, you see this sometimes in applications such as I'm trying to think, fiber optics. So like if you have a fiber optic cable, the light is just bouncing off within that fiber optic cable. That's why if you have one of those silly lamps that has all those little things coming out of it like that, that they glow really nicely because the light is just bouncing off those little cords that's in them. So that's an application of, that's an understanding of what's happening with Snell's Law. The mathematics behind Snell's Law looks a lot like this. So let me just tear this page off. So the mathematics behind Snell's Law looks like this. So Ni sine theta I is equal to Nr sine theta r. So this is actually what I call Snell's Law. So when someone says, what's Snell's Law? I say, you know, this. So these things right here, the n's, are called index of refractions. So they are basically a ratio, and they're actually equal to a formula, of the speed of light to the speed of the light in that medium. So for example, N of air is 1 because we assume air to be almost like a vacuum, like light travels the fastest in this. Whereas N of water is actually 1.33. So air travels a little bit slower in water, so that's a bigger value. So this V would be less than, so you get a number that's greater than 1. Now, if you have something that's at a critical angle, so if I bring up this diagram here for 1 second, this is my critical angle here. You can see that this angle right here is actually 90. So that's my angle. My angle of incidence is this angle here, my 49 degrees, and then my angle here would be my 90 degrees. So I should call this, I should label this stuff anyway. That's the incidence angle. So that's, you know, the first. Sometimes I call it theta 1, and this is the refraction angle. So refraction is just the bending of the light. So yeah, now if we have a critical angle, so if someone asks you to find the critical angle, the thing about the critical angle is that, and this is what you need to remember, theta r is always equal to 90 degrees. We also have to have the situation where theta or Ni is greater than Nr. What that means is it goes from a slow to a fast medium. And the reason that is because it has the bend away from the normal line for this. So remember, SFA, it has the bend away from the normal line in order for a critical angle to occur. So I reduce this formula down to Ni sine, and I call it theta c this time instead of theta I, is equal to Nr sine of 90 degrees. Now the thing about sine of 90 is that it's always equal to 1. So really, we can actually write it like this. Ni sine theta c is equal to Nr. So if I divide both sides by Ni, I actually get a really easy formula to use. Sine theta c is equal to Nr over Ni. So a lot of times this will work for you for finding your critical angle. You divide these, then you have to do inverse sine to be able to get the angle. And really, guys, that's it for the mathematics part behind it. So let's do like a really quick example of Snell's Law. Let me get a new piece of paper again. Alright, so let's say, for example, we have a medium, and light is, so this is, let's call this, let me see, diamond. And I'm going to try to remember off the top of my head that diamond has an index of refraction. I think it's 2.62. So I'm going to call this Ni to be 2.62. Now I don't know that's completely 100% certain, but I think from the top of my head, I think that's correct. And it goes, that diamond is submerged in water, so it goes from diamond to water. And let's call our Nr, water is 1.33. Now I know that one for sure. So it's going from a slow to a fast medium, so it's going to bend away, SFA. So I draw my diagram. It's going to come in here with an theta I, and it's going to bend away from the normal line just like that. So the first question I'm going to ask you guys, so if this comes in with an angle of 19 degrees what's my refraction angle? So what is my angle of refraction? So again, I'll just set up my formula. So Ni sine theta I is equal to Nr sine theta R. So now I just going to fill in all my stuff. So my Ni is 2.62. My angle of incidence is 19 degrees. My Nr 1.33, and my sine theta R is what I'm looking for. So I go ahead now and I'm going to work out what this side is right here. So I have two significant digits going on here, so I'm going to try to keep my answer to that. So sine 19, so I'm in degree mode. So sine of 19 is equal to that decimal. Then I'm going to times it by 2.62. So I'll have that as 0.853, and I'll underline that last number because it's not significant. And then 1.33 sine theta R. So divide both sides by 1.33. So I'll divide by 1.33. And then I get that guy, so I get 0.641 is equal to sine theta R. Then, when I have to find an angle using this guy, I use sine -1, so the inverse sine function. 0.641. So again, I'm keeping my numbers on my calculator just to keep it as accurate as possible. I'm not a huge fan of significant digits, so it's not really overly important for physics. People are probably going to kill me when I say that, but it is what it is my belief. And so I get an angle of refraction of 39.9, so I'll round that to 40 degrees, just like that. So there's my angle of refraction. Now let's say, for example, I want to find the critical angle. Critical angle for diamond to water. So remember that my N, for my Ni, it'd be 2.62, and my Nr is 1.33. So we don't know what the angle of incidence is this time, but we know what the angle of refraction is, sorry. It's 90 degrees. Anytime you have a critical angle, you know your theta R. So now let's go ahead and find my critical angle. So I have Ni sine theta C is equal to Nr sine of 90. So this is a formula that I generally remember. Even though you could use that other formula, you can kind of see how you can get it from this every time. So that's just 1. So I have sine theta C is equal to Nr over Ni. So when the sine theta C is equal to, so we have Nr 1.33 divided by 2.62. So mathematically, the reason why we need the Nr to be less than the Ni, or the Ni to be greater than the Nr, is that we need this number to be less than 1 because sine has a domain, or a range, sorry, a range of between -1 and 1. So we need this number to be less than 1. And that's only going to happen if the top number is smaller. So 1.33 divided by 2.62. I got 3 sig figs going on here. So I'm going to leave 4 decimals. So 7/6. And then I'll take sine -1 of that number. Just like that. So I'll do to my calculator, sine -1, answer, and I get 31. Actually, I'll call it, we got 3 sig figs, 30.5 degrees. And there it is. So any number, any angle greater than 30.5 degrees is going to result in total internal reflection. Alright guys, so hopefully this gives you a good explanation of Snell's Law. I'm going to try and make some more physics videos soon. Thanks for watching, and I'll see you guys in class. Like, share, subscribe, and I'll wish you guys good luck on any assessments you're having.